Good day, students. Good day, chemistry learners, and to those who are just watching this video as a first timer. I greet you and I welcome you to my YouTube channel. We want to quickly go to the Arrhenius equation. Before the Arrhenius equation, you need to have a good understanding about the kinetic molecular theory of gases and also a good understanding about the collision theory, which I have equally talked about in my past video. You can go to those videos, watch it, and have an understanding about what collision theory is all about. Let's go straight to to the Arrhenius equation. By Arrhenius equation, it actually explains the relationship between the rate constant of a reaction, okay, and on temperature. What I mean is the rate constant, which is K, of a reaction, and temperature. There is something that relates them together, which the Arrhenius equation is bringing about, which is the equation is K is equal to A dot E raised to the power of EA over RT. This is the equation called the Arrhenius equation. Okay, this equation explain the dependence of the rate constant of a reaction, okay, on temperature. This is the temperature and can be expressed with this equation, and this is called the Arrhenius equation. From what you are seeing in this equation, this EA is called the activation energy, okay, and the activation energy can be in kilojoule per mole or joule per mole, as the case may be, depending on the question given to you. And you have your R, which is called the molar gas constant, okay, which is a constant called 8.314 joule per Kelvin, okay, per mole. That is the unit of R, okay, joule per Kelvin per mole. Then you have your T, which is your absolute temperature, okay, your absolute temperature in Kelvin. And you have the E, this E, which you can easily find in your calculator. It is the base of the natural logarithm scale, okay. You can see it this way. So from what you have here, the parameters are given. Our A is the collision frequency factor, which is usually considered as a constant, okay, for a given reacting system over a fairly wide temperature range. Okay, the equation shows that the rate constant, if you look at it, this rate constant is directly proportional to the collision frequency factor, and therefore to the collision frequency, that is this. In addition, because of this negative sign you see here, that is the exponent of activation energy over the RT, that negative sign already it indicates something, okay, that this negative sign already tells us that as the rate constant decreases, with increasing activation energy and increases with increasing temperature. I come again. It tells us that this rate constant will be will be decreasing rather. The rate constant will be decreasing with increasing activation energy. As the activation energy is increasing, the rate constant will be decreasing, and also this rate constant will increase. It will be increasing as the temperature is also increasing. So from here, Arrhenius equation quickly tells us about the relationship between K and T. Okay, so based on this relationship between K and T, which is the rate constant and the temperature, we can easily say that if K is increasing, then the temperature will be increased, or as the temperature is increasing, K will be increasing, and vice versa. I hope you understand what I am explaining. So if you are going to relate it with the activation energy, remember your R, the molar gas constant, the molar gas constant is a constant, which is 8.314. So if you are going to relate K, which is the rate constant, with the activation energy, you will be saying that as the activation energy is increasing, rate constant will be decreasing. That it should be like that because of the negative power sign you are seeing there. That actually affects the relationship between K and activation energy, and also of course relationship between K and T. I want to believe you understand what I'm saying. So if you can write this equation in another form, okay, especially when you want to use it to solve question, you can use this if you understand how to do it mathematically. And if not, there is a more linear a linear equation you can use. If you put this, if you put logarithm to both sides, you are going to be having this. By putting logarithm to, let me use here, okay. So applying logarithm to both sides, you are going to have this, but it's better you can't work with this. So it's better you have it in this format when you turn everything to ln, such that you want to remove the natural logarithm. I mean the base of the natural logarithm. If it will be removed, you are going to have log k is equal. I mean ln k rather is equal to, this one will turn to ln A, okay? Then minus the negative sign will take effect over what? EA, which is the activation energy, over RT. This is Arrhenius equation. Okay, you can work with this, you can equally work with this. I hope you understand. Okay, there is another Arrhenius equation format you can also use. Sometimes they will give question, and the question will have different temperatures, okay, and different rate constant, and you will be asking to be looking for one of the rate constant. But before I do that, let me link this to how you can plot your graph. Just look at it and watch, and ensure you understand what I am manipulating here. So if you are going to link this to how you will plot graph, this is the Arrhenius equation. That means you are going to be having your normal equation in a straight line, which is y is equal to ms plus c. And if you have y is equal to ms plus c, with this you can see that you plot y against x. So based on what you have here now, you can see that this is where our intercept is. This is our constant. This intercept can be taken as a constant. So because of that, we are going to rearrange this formula to suit this formula. So we are going to be having y is equal to c plus ms. And remember, even this can be rearranged to give you ln k is equal to ln a, okay, minus ea over r times 1 over t. If you multiply this, you are going to have this. Okay, EA times 1 will give you EA, and R times T will give you RT. So that if you link this formula to this equation in a straight line, which means that you are going to be plotting Y against S. Okay, so here, this is our Y axis. Okay, that means our Y is equal to what? Link K, which is the Y axis, and this is our constant, which is the intercept. So our C, which is our intercept, will now be equal to what? Ln A. Okay, and then this is the slope. So this is, everything here is equivalent to this slope. So that means our slope, which is m, is equal to what? Ea minus Ea over r. Okay, everything including this negative goes with the slope, minus Ea over r, and our 1 over t, which is the x-axis. Okay, that means our x-axis will be what? 1 over t. What does this thing teach us? It teaches you that when you want to plot the Arrhenius equation graph, okay, you are going to be plotting of a graph of ln k against 1 over t, just as you have a graph of y against s. So you'll be having graph of ln k against 1. So in your y axis you have ln k, while at the s axis you have 1 over t. So when you are giving data, in your data you are giving k, and t, the rate constant and t. Your own is just to look for 1 over t, the inverse of the temperature. Then it gives you, you have your table of data, then you plot a graph. Actually, when you plot the Arrhenius equation graph, you are expected to have something like this. It's a linear graph, a straight line graph that will go this way. And when you have that, then this place becomes your intercept. And how do you obtain your intercept? So this is our intercept. And what is our intercept? Here is lane A. So you have lane A here as your intercept. That means in your graph, whatever you obtain from your graph, whatever value you obtain from your graph here, the straight line that cut the y-axis, whatever you obtain here is called lane A. That means if what you have here, for example, gives you lane A is equal to, is giving you, for example, please, this is an assumed value. For example, you have let's say 0.9. That means your A now will now be inverse, lane inverse of 0.9. You press this in your calculator, you now get the value of collision frequency factor, because whenever you are given table of data, you will be required to look for the collision frequency factor, okay, and you will be required to look for your rate constant, and this is where you can obtain those information. How do you get your slope? Remember your slope is what? Minus EA over R. You will even be required to look for your activation energy. So this is my slope. You draw a triangle on your straight line like this, okay. You draw a triangle on your straight line like this. So you can see now that your slope comes out as you have your slope, which is minus EA over R. It will be equal to whatever you obtain here as your Y2, okay, Y1, S2, whatever you obtain will come out here. Let's say, for example, you obtain 0.3, okay, as your slope. Okay, so with that, you can obtain your activation energy, which will now be minus EA. Please understand that this is an assumed value over our rate constant, which is 8.314, is equal to 0.3. So you can have minus E is equal to 8.314 times 0.3. So from here, you get your activation energy. By the time you cross multiply, then your activation energy will give you a particular value here. That is how you can obtain your activation energy and your collision frequency factor. Okay, after obtaining that, you have actually gotten virtually everything you are looking for. Do you even know you can get your K, your rate constant, from here? You can actually get your rate constant, okay, at any inverse of the temperature that may be given, okay. So for example, you are asked to look for the rate constant at at temperature of 300 Kelvin. Please understand, if you have in any place here temperature of 300 Kelvin, whether it's present or not, that means your exercise have to be increased to such temperature. But what you will do is that they have given you a temperature of 300 Kelvin, and you know here you have 1 over T. So what you are supposed to do is to first of all look for 1 over T and say 1 over 300. Whatever you obtain here, you will look for the corresponding value here, okay. Whatever you obtain here, for example, you'll be obtaining 0.0. So you will be obtaining a value like 0.03. That means here, the inverse of the temperature, you will go and look for 0.03 here. Let's say you find your 0.03 at this point. You will have to take it to where you have this your straight line, and link it to this point where you have the link K. And whatever value you obtain from the link K, let's say you have link K is equal to 2.5, for example. Please understand, this is an imaginary value. Or let's say 0.6. If that is what you obtain, then it's for you to say K will be equal to ln inverse of 0.6, and then you obtain your rate constant at a particular temperature, okay. And understand, when the temperature is given to you at that particular temperature, you are expected to get the inverse of that temperature so that you can locate it on the x-axis, okay. Further question that can be asked will be to determine the activation energy, though I've talked about that, to determine the activation energy, okay, graphically. And how you get about that is that after you are done, you get your slope. From your slope, you have your rate, your molar gas constant, and from here you can manipulate your activation. I've actually talked about this, so ensure you try to understand. If you do, ensure you show some I actually want to believe you do have an understanding on this topic now. If you do understand, please share to other of your colleagues, your friends, and students, learners of chemistry, and share to teachers, so that the study in chemistry can spread. The knowledge in chemistry, the understanding in chemistry can spread to others who are trying to understand. Thank you. Please ensure you share this video to others. Thank you, and God bless.